First of all, thank you, Altair, for letting Clemson come and present. Again, I'm the Infrastructure Manager at Clemson. My job role is to put clusters together, make sure they work, make sure our users are happy. So I manage a small team of about 5 system admins. And I'd like to go ahead and give a call out to 2 in particular. Corey Ferrier, she's our local PBS expert. So she's the one that actually watches PBS, but from day to day, make sure everything works. Also, Paul Walkowitz, I'll talk about this a little bit in the presentation. He actually worked with some of the node provisioning hooks in PBS. So we'll talk a little bit about that. So first of all, I'm going to give you a little history of HPC at Clemson. First of all, we have the Palmetto cluster. The Palmetto is the actual name of the state tree, so that's where the name comes from. We put it together in 2007. Currently, it's over 1,700 nodes, roughly 14,256 cores. Roughly, all of those machines are connected via 10 gig nearnet for the fabric. We also just got in some new Sandy Bridge nodes. All of those are connected with the new InfiniBand FDR fabric from Mellanox. We have a couple of different file systems on the cluster. We have 240 terabyte home space, project space for the users. We also have 240 terabyte scratch storage space running the OrangeFS file system. Currently, the Palmetto cluster is number 194 on the top 500 list. It's roughly around 96 teraflops. It's been as high as number 60 on the list. And originally, when we put the cluster together, we used the Torque in Maui for the job scheduling. It worked fine for the small number of nodes we had, but as we grew, we quickly outgrew the capabilities of that scheduling system. In October of 2011, we migrated to PBS Pro 11.1, and we'll talk a little bit about some of the things we had to do to support our Condo model. That's the scheduling philosophy that our cluster revolves around, so I'll talk a little bit about that. So what I mean by the Condo model is we call it the condominium model. So before 2007, before we had the cluster, we had a few little mini closet clusters sprinkled about on campus at various places. So when a faculty member would get a grant, they would actually buy their own little cluster, put it in a closet somewhere. They would hire graduate students to learn how to do HPC and manage it. That didn't really make sense, especially when Clemson's a state-supported university, and as we all know, there's lots of budget problems everywhere. Clemson is no different. Our budgets are being cut, so it really makes sense to try and share costs wherever possible. And one of the ideas was combine all our HPC resources across campus and build one giant cluster that all of campus could use. So the way we do this at Clemson, we have people that want to buy nodes, and the university actually matches their purchase by supporting and buying the racks, the PDUs, all the networking equipment, networking cards. So the faculty member, all they have to do is buy nodes, and they can plan for this in their budgets and put this in their grant proposals. And another great thing about this is you have a professional set of system admins that know how to put HPC systems together and maintain it. So the faculty members no longer have to pay a grad student to put a cluster together and learn how to run it. They can actually pay the grad students to do the real research activities. Another reason we went to this condominium model is to promote efficient use of idle cycles. Traditionally, if you had a closet cluster, you may use it 40%, 50% of the time, but the rest of the time, you have all those idle cycles just being wasted. So by gathering all these HPC resources together, we can actually run backfill jobs on the cluster and actually fully utilize the resource. And we have this concept of owners and general users in the Condo model. People that actually buy node resources, they become known as owners. So they get their own queues and they get preemption rights based on the number of machines that they have purchased. General users are users that can just log into the cluster and submit jobs. They haven't purchased anything, so they get first come, first serve in the general queues. Any unused cycles in the cluster, we actually backfill with a system called Condo that's from the University of Madison, Wisconsin. So users can submit jobs through the Condors, and those run whenever the cluster is not being used. So going back to the Maui and Torque scheduler, we originally implemented that. But we did run into problems, and the problems grew as our cluster expanded. One of the big things about Maui was the entire resource scheduling was single-threaded. And commands such as the show queue and check job commands, they would frequently hang for users and time out, so they couldn't get adequate job information about what they have running. And it would really annoy the users, so they were constantly reporting these problems to us. Another problem we ran into was that Maui would routinely hang if a user submitted lots of jobs all at the same time. And we do have a few groups that like to submit thousands of jobs at the same time. So this was becoming a frequent problem, and it would cause serious job start delays because the schedule would have to go through all of those things one at a time. Another sore point was that reservations did not work properly. We were never able to get the reservations to work with Maui and Torque. We actually had to do manual reservations. We would set a separate queue up manually for any kind of specific reservations that we needed. Preemption was also not reliable with Maui and Torque. Sometimes it would work, sometimes it wouldn't, and there wasn't a clear indication as to why it wasn't working in the logs. Also, one really strange problem that we discovered, if you added extra nodes and you put them in your etc host file, we actually synced all of those files across all of our cluster. Occasionally, that would really confuse Torque on the nodes for some reason. That was just really weird. And also, there was limited documentation on the Maui and Torque system. And some of the documentation, they would describe features that weren't implemented. So after all of those problems, we decided Clemson needed a better scheduler. So that's when we started looking at the alternatives. We looked at things like Sun Grid Engine. It looked promising, but it would have been a big learning curve for our user population. They were used to using PBS, and we didn't really want to have to retrain our users, so we quickly ruled Sun Grid Engine out. We did look at Moab. It also looked promising, but the more questions we asked, we were not convinced that it was going to solve the large number of simultaneous job submits. So we then looked at PBS Pro, and that is what we ended up going with at Clemson. Talking about some of the migration efforts to PBS, one thing we did, we packaged an RPM file for the scheduler. So that's actually how we installed it on all of the compute nodes and the submit nodes. We still use the PBS/install script to do the actual installs on the server and the scheduler node. We do use epilogue scripts and prologue scripts to turn off our Condo backfill. So when a PBS job lands on a node, it automatically terminates any Condo jobs that are running on that node and turns off Condo so it can't accept any new jobs. And when the PBS job finishes, it turns Condo back on so it's eligible to run any backfill jobs. We also wrote a PAM module because we don't want users to log into the nodes unless they have an actual job running on that node. So that's just one thing that we had to write ourselves. Also, there were a few functional differences we discovered between Maui and Torque and PBS Pro. One is Maui used a quality of service for the preemption rights, whereas PBS Pro uses priority queues to handle the preemption. So that we really had to rethink how we did preemption moving to PBS Pro. Another thing that we noticed, this was after the implementation, that PBS Pro did not support the Q sub -X to do X redirection. We're happy to report that was fixed in 11.3 that we've recently moved to. Also, we had to modify a PBS top tool. We use that a lot on the cluster. We've trained our users to use this utility, and it's just a curses-based command line utility to show how the jobs are being run on the cluster. And actually, this next screen actually kind of gives you a good view of what the PBS top utility looks like. So each one of those, you can't really see it, but there's little dots. Anywhere you see a dot, that's a core that's not being used. And all the different colors represent all the jobs that are being run on the cluster. We do have a mixture of jobs types on the cluster. We do have a lot of what we call embarrassingly parallel jobs using just one core. And we try to stack those. You can kind of see the colors. It's got a lot of different colors in there. We try to stack those as close together as we can so we can get full utilization of all the cores on the nodes. But this is what a lot of users are used to see actually how busy the system is, and they can actually monitor their jobs using this utility. Also, we had to write a few hooks for migration just to do some things that we were used to doing in Maui and Torque. One of the ones we wrote was we actually called it ACL group sloppy. That's a setting that was in Maui. So essentially we set up groups for all of the owners in the cluster. So we want them to have their group rights when their job runs. So this was a little hook that actually sets the group to the right thing. Otherwise, the users would have to specify that on the command line as they do their Q sub. So we would try, and our whole philosophy is we don't want the users to have to do anything that extra. We just want them to submit their job. Any kind of defaults like this, we want to do for them. Also, we had a force rerun hook that we wrote because our whole scheduling philosophy is designed around preemption. If a general job is running on the cluster and an owner job comes in and there's not enough resources, we want to preempt some of those general user jobs. But we want those jobs to get forced to rerun again at a later time. So we did not want to have users, we didn't want to force users to actually do the force thing on the Q sub line. So we actually changed one of the hooks to actually do that for them. So any kind of job that comes in, we automatically force it to be rerunnable. We also created a mail address hook because there's no mail domain in PBS Pro. So if a user wants notification, if they just put their user ID and they don't fully qualify it with a domain, we actually tack a domain onto that email address. One thing that we discovered, this was fairly recent, we did have a few routing queues that we implemented, but we're heavily using routing queues now. One thing, all execution queues, or both owner and general, they all have a front-facing routing queue. And the reason for that is that we've discovered, because we noticed there were some delays in the preemption, and we discovered if you have a lot of waiting jobs in the execution queue that are waiting to run, that actually slows the scheduler loop. So if you keep those jobs that are waiting to run in a routing queue, the scheduling loop inside PBS runs much more efficiently. So we've changed all of our queues to have a front-facing routing queue for that reason. And overall, we try and keep our cluster utilization at around 90%. Sometimes it's even higher than that, but that's usually our target is 90% on our cluster. And this graph right here shows the number of jobs actually queued in a routing queue. That's the green, and the you can't hardly see is this little line right there. That's the actual jobs queued in the execution queue. So you want to keep those as small as possible in the execution queue because that will help speed up preemption. And then the light blue at the top up there, that's the actual jobs that are actually running on the system. Okay, this is kind of the how a general user job works on our cluster. We start out, I'm sure you can't read any of this, but I'll kind of point things out. Users submit to a routing queue the Workq, and it's a routing queue, and then we've got 23 execution queues under that. And each execution queue depends on the wall clock time and the number of cores that the user has requested. So we've got 23 of those little execution bins, so to speak. So a job will, once it gets into one of these, we can actually tweak the knobs. That's the big reason why we split it up into this many queues. This gives us a little bit of fine-grained control. And one of the big reasons we did this, we really wanted to use the fair share capability inside PBS Pro, but the one thing that kept us from using that is it's a global fair share, which we couldn't do because we have to guarantee that our owners are never preempted. So this kind of gives us a manual fair share, so to speak. So this graph here just kind of shows a couple of those little execution bins running under the Workq. So you can tell by the workflow here, we have a lot of single core jobs running. This is just a snapshot on a particular day. We have a lot of single core jobs. And then with the orange up there, we had a lot of single node jobs. But again, we do have a various mix. That's just how it was on that one particular day. This next graph kind of shows how we can control the fair share using all of those 23 different execution queues under the routing queue. So this is an ideal situation here. We want to be able to let jobs in from all of these queues. So we don't want we don't want all of the single core jobs to monopolize the system. So we can actually turn the knobs on these execution bins to say that we only want X number of these jobs to run. So Corey, my system admin, she's constantly watching this and trying to make sure that everything's kind of running smoothly across all of these queues, and she'll back certain queues down on the max jobs running and turn other queues up higher. So this is kind of our fair share, manual fair share that we did on the cluster. This is just this quick sample of one of our execution queues for the Workq routing queue. So really the only thing here I was wanting to point out is we do set the max in CPUs and the min in CPUs, so we kind of contain what can actually get into this bin. And we also put caps on the memory on there. And we don't lock the memory down. We actually tried locking the memory down to on the node really tight and ran into problems because the users had a lot of misbehaving applications. So some were using more memory than they should have been. So we kind of had to bump that up higher than what we would have liked. But that's just a case of living in the real world. Not all the applications are well behaved. RQ policy. Each owner gets their own express queue that's accessible by their group members. The size of these queues depends on the number of nodes they purchase. So we'll actually lock down that queue to, if they bought 2 nodes of 16 cores each, they can only execute 32 cores in that queue. So it all depends on how many they've purchased. All owner queues have the same priority, so no one owner is more important than any other owner in this system. Owner queues get a max dwell time of 168 hours. The general queues only get 72 hours max dwell time. And that is just an arbitrary number. That's 168 hours is a week's worth of time for the owners. We wanted to lock that down because we did not want users to run jobs for a very long period of time and then a node goes down and then they've lost all their work. So we've kind of enforced with our users, and we publicize this in our training classes, that we really want users to do checkpointing so that way they don't lose a lot of work, because we don't want these cycles to go to waste. Owners that have purchased the new Sandy Bridge nodes, we actually treat a little bit differently. They actually get a flop 4 execution queue and a flop 8 execution queue. And what that's about, the older, like Westbury nodes, they actually run, they could do 4 floating point operations per clock cycle. The new Sandy Bridge nodes have double that. They can do 8 floating point operations per clock cycle. So we thought long and hard, should we make a separate cluster for these Sandy Bridge nodes, or do we just want to keep it all one cluster? So we decided we're just going to keep everything one cluster, but we'll just queue them differently. And also our CTO recognized that these Sandy Bridge, since they're very new, are very expensive. And some of the faculty members were asking why our node costs are going up. So we had to explain to them these nodes, yes, they're more expensive, but they can do twice the amount of floating point operations. So as a perk to our owners, if you purchased the new Sandy Bridge nodes, we gave you double the cores on the flop 4 nodes, the older nodes. So you could run in either the flop 4 nodes or the flop 8 nodes. So that gave our owners some flexibility and also helped them get past that dollar figure cost. But that also makes the schedule a little bit more complicated, because now we've got 2 different queues and we have to figure out which one do they run under. So we did have to do some magic with some routing queues to make this work. And I don't know if you can read that up there. But essentially, a user submits their job to their normal routing queue. And they can tag in their job, they can say flops equals 8 in their job. And then we've got a hook that actually looks to see what the value is of that flop attribute. And if there's no flop attribute, it defaults to flop equals 4. So then it looks and sees if there's any free resources in whichever queue that it ends up. And if it's able to execute, it'll immediately put it in the flop 4 execution queue or the flop 8 execution queue. And another great thing about the routing queues is you can hide all of this scheduling complexity to the normal user. They don't see any of this. They submit to their same routing queue. They don't know the difference. And this is kind of an owner job flowchart. So at the top, the owner submits a job to their routing queue. And then our hook looks to see if a flop is specified. And if it's not, then it goes over here and it'll add flop equals 8 to the job. And then it checks to see if the flop equals 4. If it does, it comes over here and looks to see if there's any free cores in the flop 4 execution queue. If there are not any free cores, it just keeps waiting in that routing queue until resources are free and it can run. So it drops down here into the flop 4 execution queue once resources are available. And if it needs to, it'll actually preempt the general jobs. And the same works on the flop 8 side. It'll just sit there and wait in a routing queue until those resources become available and preempt as necessary. The next topic I was going to talk about was the PBS provisioning hook that we played with. We used a product from Dell called the Advanced Infrastructure Manager, and it's really just a cloud provisioning service. You can create images that run on bare metal or in a VM or both. You can actually migrate the image between on the fly with the pivot booting. So we were actually looking at this to simplify some of our data center deployments. So we thought, okay, what could this do in an HPC environment? So we started playing with the PBS provisioning hook just to see what it could do. And we actually showed this at SE11 last year. And just to kind of give you a brief overview of what AIM does, it kind of encapsulates an image. They call it a persona. So that's the image itself and its settings. And AIM itself has no direct API, so you have to actually build a file with the commands, and you actually have to feed these commands to an SDK utility that this product provides. And this is how you tell it you want to start an image or stop an image. So that's the kind of methodology. So we did have to code one of the Python hooks. So one of the things it does, it checks to see if the AIM persona is active, and if it is, it'll actually send a command to stop it and actually shut down the compute node. I guess I should back up. First of all, a user submits a job, and in that job it actually has the OS they want to use. So we actually tie that in with this hook system, so you can actually stop a node, re-image it on the fly with this. If the persona was stopped or if it was not active, then a command is sent to AIM to start it. So it's always starting with a fresh image. So if it was previously running, it'll stop it and restart it. And then the hook will actually send messages back to be reported whether the operation was successful or not. And the hook I already mentioned this, that we demoed this at SE11, and there's actually a video. I wasn't sure if I'd have time to show it, so I didn't include it. But there's some links here. You can download this presentation from the PBS website and go to that link, and you can actually see it in action. And that's the video we took at the SE11 last year. And I also have the code out there on the network provisioning hook if you actually want to see what the code looks like for that. So overall impressions of PBS over the last year and a half, we've been very impressed with PBS support. They've been very helpful, very responsive to any questions that we had. Altair also offers some very good training classes. I had Altair actually come on site and give all of my system admins a 3-day class, and it was very informative, and it was I really highly recommend it. Also, overall, it was a very easy transition to Maui and Torque. Of course, we did our homework ahead of time. We actually tested it on a test cluster to make sure we understood the operation of it. But amazingly, we had very few user complaints about things that had changed. Also, the advanced reservations in PBS Pro works great. That's the one critical feature that we were missing with Maui and Torque, and it works just like it says it does. So that was a really good thing. Also, the dedicated time feature has proved very useful during our cluster maintenances. So we can actually set dedicated time, and then only jobs that fit within the time window before the maintenance actually get dispatched and run. So that's really nice. We don't have to manage that by hand like we did before. A few areas of improvement that we've noticed lately that I wanted to mention was that job comments, if you do a qstat-xf, sometimes those job comments are just bogus. Most of the time they're right, but occasionally they're wrong, and that has caused some confusion for some of the users. So that might be something that could be looked at to improve on that. And also the fair share per queue idea. would be a very useful thing to have in the scheduling system. Right now, we're doing the manual fair share, but we'd love to have that automated. And until we have it on a per queue basis, we won't be able to do it. And that's it.